Hello everyone, in this video we're going to be learning about electric fields. Let's first learn about what a charge is. Charge is a characteristic of electrons and protons. It is associated with a variety of electric properties, which we will not cover, but we know that it exists, and its units are C, which stands for coulombs. Both electrons and protons have 1 point times 10 to the negative 19th coulombs in them. Ions possess charges as well as protons and electrons. Now, let's talk about conservation of charge. Although the individual charge on any one object in a problem may vary, the total charge of all the objects will remain constant in closed systems. Let's talk about charging. There are two main types of materials that either hold or do not hold electricity. So conductors hold their electrons loosely, which causes to an electric flow. A good example of conductors are metals, such as copper or gold. Insulators insulate, so they hold their electrons tightly, which causes to no electron flow, which is no electricity. And plastic is a good insulator. There are two main methods of charging. One of them is conduction, which involves physical contact of, for example, two iron balls, and induction, which is done without physical contact. Now, let's look at this question. Two neutral uncharged conducting spheres mounted on insulating stands are in contact with each other. A negatively charged rod is brought near the spheres but does not touch either sphere. How can the spheres both be charged, and what will the sign of the charge be on each sphere? So we see examples of both conduction and induction here. So here, these two balls are touching each other, so we can think of them as a closed system or one material, because right now they're in a conduction position. This negatively charged rod is inducing, so it's doing induction, and it's attracting the protons to come to the sphere that is close to it. As a result of that, the electrons are on the other sphere. Well, here you might be thinking protons and electrons are not actually moving around because protons obviously don't move around. But here, the electrons are moving to the sphere on the right, so that the number of protons on the left are much bigger. And when conduction ends, so these two separate out, what's going to happen? Well, they're going to keep their charges. So the left one is going to be a positive one, and the right one is going to be negative. Now, let's talk about Coulomb's law. Coulomb's law is helping us to find the force between two charged objects, and the resulting force acting on each charge can be determined using Coulomb's law. So say that we have two charged objects, okay, and here another one. So this one is an electron too, and this is a distance between them, so r. Here we see that k times the charge of the first one, so this one, and the charge of the second one over the distance squared. Here, the letter K indicates the electrostatic constant, which is equal to 9 times 10 to the 9th newtons meter squared over Coulomb squared. Well, right now you might see some resemblance. Doesn't it look like the formula F equals G m1 m2 over r squared? That's because the forces in fields act all the same, and they have very similar formulas actually. So this formula is used for the gravitational force, while this formula is used to find the electrostatic force. Now, let's talk about electric fields. As we have said, they're pretty close to gravitational fields, so they have very similar formulas again here too. So the formula for a mass in a gravitational field is m times a, so mass times the acceleration, is equal to the gravitational force. Here, the Q, which is the charge times the electric field, is equal to the force. So if we happen to place a charge here, its force is obviously equal to Q times E. And E is usually given us in uniform circular motions, at least in high school physics, but we'll learn about how to calculate the electric field of spherical objects. And usually in electric field questions, the gravity is ignored. But if it is not ignored, for example, in the case of Millikan oil drop, so if we assume that this electron is stationary here, then Fe has to be equal to Fg. And Fe is Q times the electric field, and Fg is equal to mass times the gravitational acceleration. So in order to find the electric field here, for example, just send the Q to the other side of the equation, and E is equal to m times G over the charge. So for example, if you have an electron in an electric field and you want to find what the electric field is, and you know that it's stationary inside of an electric field, then you can use this formula to find the electric field. Spherical point charges are charges where the electric field is calculated as though it originates from a single point in space. So that's just an assumption. And the electric field is found by K, which is the electrostatic constant, the charge of the sphere, and the distance in between the point in space where you want to find the magnitude of electric field of this spherical object. Spherical point charges create their own electric fields, just like here. And here, the vectors are incredibly important. So if you look at here, we can see that the positive charges have electric fields that is going from them to the outside, while the negative charges have electric field vectors coming at them. This is really important. In the situation of two charges, here the electric field changes like this. So if you have two positives, they kind of want to go out like this, and they don't want to go into this direction because there's obviously another one which can't go in this way. So this vector can't go in this way because this is not negative, so it has to repel to the other side. And on the situation of negative charges, it just goes to them, the vectors. And if there's a positive and negative one, the vectors go from the positive to the negative one. By looking at the formula of spherical point charges, you might also realize that if you put another Q here, you actually get the force. So E times the Q is equal to the force. So when there's an electric field, you want to find the distance between the two charges, and you want to put them into the equation, and it's going to give you the force because of Coulomb's law. Now, let's solve this question. A charge of positive 6 times 10 to the negative 6 coulombs is brought near a negative charge in a region where the electric field strength due to the negative charge is 20 newtons per coulombs. What are the magnitude and direction of the force acting on the positive charge? So from the formula F equals QE, we can easily find the force. So let's do it. The charge is 6 times 10 to the negative 6, and the electric field is 20, and this gives us 1.2 times 10 to the negative 4th newtons as the force. But what is the vector? So we know that the vector, now let's solve this question. A positive 8 Coulomb charge is located 2 meters to the left of the origin, and a negative 4 Coulomb charge is located 2 meters to the right of the origin. Determine the magnitude and direction of the electric field at point P located at the origin. So firstly, let's find the electric fields individually. I'm going to start with the positive one. So E equals K times Q over R squared for both of them. Let's plug in the numbers. So electric field 1 is equal to 9 times 10 to the 9th. So this is a constant times 8 coulombs over 2 meters squared, and this gives us roughly 18 times 10 to the 9 newtons over coulombs. Now let's find the second electric field. So electric field 2 is equal to 9 times 10 to the 9th, which is the constant. The charge is 4 coulombs over 2 meters squared, which gives us 9 times 10 to the 9th newtons over coulombs. Now let's find the electric field in point P by simply adding these two electric fields together. 9 times 10 to the 9th, which is going to give us 27 times 10 to the 9th newtons over coulombs. So you know what the magnitude is going to be. But let's look at the vectors and the reason why we simply added them. So the electric field that is caused by the positive charge is going to be in the right direction. So in this way. And the electric field that is caused by negative charge is also going to be in the right direction. So they're actually going in the same direction as vector quantities. And that's the reason why we added them together. If they happened to be repelling each other, so if they had the same signs, we would have subtracted them. Here's another type of question that you might face a lot in this topic, so let's do it. Two negative charges, 4 coulombs and 16 coulombs, are separated by a distance of 1 meter, as shown in the diagram above. Determine the location as measured from 4 Coulomb charge where the electric field is 0. So we have to find an electric field, so we have to find a position in the electric field that the electric field is going to be zero. Well, it's probably, well, in order to find a point like that, you would assume that the point where the electric field is zero is going to be somewhere close to the -4 Coulomb charge. So around here, right? Because the magnitude of it is a lot less, but no matter what, we have to find it either way. So let's just call this distance r and this distance 1 minus r because the total distance is 1 meters. In a point where the electric field is zero, the sum of two electric fields have to be zero. So we can easily infer that they're going to be equal to each other but in different directions. This is why there's a minus sign here, because they are in different directions. So they're going to repel each other. Now let's plug in the numbers. K times 4 coulombs over r squared is equal to K times 16 coulombs over 1 minus r squared. So we're going to take the square of the whole thing. We're going to simplify the case and take the square roots of both sides in order to get rid of the exponents. So this is 2 over r is equal to 4 over 1 minus r. And we're going to Cartesian multiply these. So 4r is equal to 2 minus 2r, and 6r is equal to 2. As a result of that, we get r equals 2 over 6, which simplifies down to 1 over 3. We know that the whole thing was in meters, so this is just going to be 1/3 of the road till the electric field is equal to 0 from the 4 Coulomb charge. So this is roughly 0.3 meters here, maybe 0.33, and then this part is 0.66 meters. Thanks for watching this video.